Prova.
It can be zero distance, bringing solar energy to every corner. It can be zero error, representing our attitude to the products. It can be zero destination, representing our pursuit of advanced HJT technology. It can be zero carbon, contributing to build a cleaner world. So what exactly is zero? Zero is the goal. A goal that drives us forward, fuels our passion, and defines our purpose to shape a net zero future. Zero is everything.
Since 2008, Glasmanufaktur Brandenburg GmbH, as part of the Interfloat Group, has been producing high-quality glass for photovoltaic and solar systems, as well as for greenhouses at their Czernitz site in the south of Brandenburg, a historical glass-making region. 365 days a year, high-quality glass paints are produced from sand, dolomite, soda, cullets and other raw materials. More than 300 employees, as well as up to 60 temporary agency workers, work for GmbH, making it one of the region's most important employers. To produce high-quality, low-iron glass, it is necessary to use premium raw materials. Being a supplier for GmbH requires auditing according to ISO 9001. In the batch house, the raw materials are weighed and mixed following the company's own recipe. Batch feeders then carry the finished batch in the melting tank. In the melting tank, the batch is melted to a liquid mass at up to 1600 degrees Celsius. To this end, the GmbH melting tank is fired using natural gas and oxygen. This is currently the most environmentally friendly firing method for melting tanks and sets us apart from our competitors. Highly qualified employees monitor the production processes in the control room. The liquid glass is fed continuously to the two production lines where, at a temperature of around 1000 degrees Celsius, it is discharged onto the rolls with a width of 2.4 meters and a height of approximately 7 centimeters. Standard glass thicknesses are 2, 3.2, 4, 5 and 6 millimeters. Different glass patterns enable different applications. The pattern of the glass minimizes reflection, meaning the sunlight is guided into the glass and thus onto the PV or solar module. After rolling, the temperature of the glass is reduced to around 80 degrees Celsius by transporting it on water-cooled transport rolls and ceramic rolls so as to ensure break-free cutting. The edge cutters score the side edge strips and then break them off. The cross cutter splits the glass ribbon into stock plates. The first inspection takes place during this step of the process. The position and size of defects, such as bubbles or seeds, is registered and evaluated. Two fully automatic and computer-aided cutting lines make optimum use of the glass ribbon for each blank. This enables even small production series to be produced according to customer wishes. For finishing, lines are able to flexibly accommodate the individual wishes of our customers. GmbH consistently seeks to further develop innovative products and improve the production process. A team of young, motivated engineers works closely with production engineers to analyze the current process. For our customers, the strength of the glass is very important. After all, the products must endure extreme weather conditions such as severe hailstorms. To achieve this, the glass is reheated to a temperature of over 600 degrees Celsius and it's thermally toughened with huge amounts of cool air. Only top-quality products leave the works. Therefore, the automatic packaging line is subject to constant visual monitoring. In the packaging line, the glass is automatically rotated into the position required by the customer and then washed. After another automatic inspection, the separating layer made of paper or cord is applied only to the best glass parts. These are then packed automatically, either on L-racks or in so-called flat packs. A final visual inspection takes place manually. The finished packaging is covered with stretch film and is released for dispatch. Products for our customers are stored in an area of 13,000 square meters. In this way, the Interfloat Group ensures maximum flexibility and continuous supply capability. Our products are an important component of the photovoltaic and solar modules of all major European manufacturers. The glass that we produce protects plants and promotes their growth in greenhouses all over the world. The Interfloat Corporation's investment in GmbH Glasmanufaktur Brandenburg created an economic beacon in a structurally weak region. This was acknowledged in 2016 with the European Solar Prize. We are proud of our company and look forward to a bright future. GmbH, High Performance Solar Glass.
As the global climate challenge grows, the development of photovoltaic PV new energy is of great urgency. In 2006, Tongwei entered the PV new energy industry and has now become an integrated PV enterprise, engaging in the production of high-purity crystalline silicon in the upstream, high-efficiency solar cells and modules in the midstream, as well as the construction and operation of PV power stations downstream. With its leading advantages in scale, technology, cost, and quality, Tongwei Solar has formed a vertically integrated and complete PV industry chain. Tongwei Solar is accelerating towards an integrated layout and has now arranged the layout of module production bases in Hefei, Yancheng, Nantong, Jintong, and other places. After years of technical accumulation, scientific research, and innovation, Tongwei Solar now has two major series of module products: half-cell modules and shingled modules. Half-cell modules have advantages including low LCOE, high power and high gain, while shingled modules are featured by high power efficiency, safety and reliability, low lead and zero fluorine, and convenience of recycling. Tongwei Solar is also promoting TNC and THC technologies in parallel and actively exploring various cell and module technologies such as TBC, perovskite lamination. Tongwei Solar has independently developed the TNC high-efficiency cells, the mass production conversion efficiency of which has reached over 25.4%. Among the leading manufacturers that have taken the lead in entering the HJT field, Tongwei Solar's HJT cells have achieved a maximum R&D efficiency of 26.07%. Tongwei Solar continues to update its technology pool with emerging ones and always stays at the forefront of the industry. Ranking on the Tier 1 list, it has currently obtained national and regional certifications in major markets such as Australia, Japan, and France. Tongwei Solar's high-efficiency modules are suited for household rooftops, industrial and commercial distributions, large ground power plants, etc., boasting a perfect and professional service system and a high standard of supply quality. Tongwei Solar can meet global customer needs in all respects. Tongwei Solar's high-efficiency modules have cooperated with multiple projects around the world. Its products are exported to more than 40 countries and regions such as France, Germany, the Netherlands, Chile, and so on. Carbon peaking and carbon neutrality goals have become a global consensus. EV brings together the momentum for green development to create a better future and achieve the
Manufaktur Brandenburg GmbH, as part of the Interfloat Group, has been producing high-quality glass for photovoltaic and solar systems, as well as for greenhouses at their Czernitz site in the south of Brandenburg, a historical glass-making region. 365 days a year, high-quality glass paints are produced from sand, dolomite, soda, cullets and other raw materials. More than 300 employees, as well as up to 60 temporary agency workers, work for GmbH, making it one of the region's most important employers. To produce high-quality, low-iron glass, it is necessary to use premium raw materials. Being a supplier for GmbH requires auditing according to ISO 9001. In the batch house, the raw materials are weighed and mixed following the company's own recipe. Batch feeders then carry the finished batch in the melting tank. In the melting tank, the batch is melted to a liquid mass at up to 1600 degrees Celsius. To this end, the GmbH melting tank is fired using natural gas and oxygen. This is currently the most environmentally friendly firing method for melting tanks and sets us apart from our competitors. Highly qualified employees monitor the production processes in the control room. The liquid glass is fed continuously to the two production lines where, at a temperature of around 1000 degrees Celsius, it is discharged onto the rolls with a width of 2.4 meters and a height of approximately 7 centimeters. Standard glass thicknesses are 2, 3.2, 4, 5 and 6 millimeters. Different glass patterns enable different applications. The pattern of the glass minimizes reflection, meaning the sunlight is guided into the glass and thus onto the PV or solar module. After rolling, the temperature of the glass is reduced to around 80 degrees Celsius by transporting it on water-cooled transport rolls and ceramic rolls so as to ensure break-free cutting. The edge cutters score the side edge strips and then break them off. The cross cutter splits the glass ribbon into stock plates. The first inspection takes place during this step of the process. The position and size of defects, such as bubbles or seeds, is registered and evaluated. Two fully automatic and computer-aided cutting lines make optimum use of the glass ribbon for each blank. This enables even small production series to be produced according to customer wishes. For finishing lines are able to flexibly accommodate the individual wishes of our customers. GmbH consistently seeks to further develop innovative products and improve the production process. A team of young, motivated engineers works closely with production engineers to analyze the current process. For our customers, the strength of the glass is very important. After all, the products must endure extreme weather conditions such as severe hailstorms. To achieve this, the glass is reheated to a temperature of over 600 degrees Celsius and is thermally toughened with huge amounts of cool air. Only top-quality products leave the works. Therefore, the automatic packaging line is subject to constant visual monitoring. In the packaging line, the glass is automatically rotated into the position required by the customer and then washed. After another automatic inspection, the separating layer made of paper or cord is applied only to the best glass parts. These are then packed automatically, either on L-racks or in so-called flat packs. A final visual inspection takes place manually. The finished packaging is covered with stretch film and is released for dispatch.
Okay. C'è Andrea. So, good morning everybody. Can you have a seat please? we are slightly delay. Okay. So, my name is Antonio Terrasi. I'm professor at the University of Catania, and with my friend and colleague Cosimo Gerardi from Trisan, we have the pleasure and honor to open this workshop. Just a few words. I mean, my duty is just to give you a very warm welcome to Catania. I hope you. I'm not responsible for the weather. I'm sorry. So usually we have much better weather also this period of the year, but this is not on my show. So tomorrow you will also see my rector, Professor Francesco Priolo, which is unfortunately he apologized, but today is busy with a very another commitment, so he will be here tomorrow because he's also a physicist, so he will really appreciate this conference, this workshop. So welcome this magnificent location of our university. This is the Human Science Department, but it's so beautiful and so big that we often use it also for scientific meeting and congress and workshop, as in this case. So I'm pretty sure this will be two very dense days of state of the art concerning this specific technology and concerning the solar energy in general, the photovoltaic in general. And so I'm very curious and very excited to learn something myself. I work in photovoltaics, but in a very specific field, which is a TCO, so I will pay attention to this in particular. But I saw the program, and we decided to have a really expert from the academy and from the industrial world on this wonderful, probably, future for for the humankind, which is the solar energy. So I stop here. Once again, welcome. Anything which will be bad is under my responsibility. Everything which is good is because of them. And I give the microphone to Cosimo Gerardi. Thank you so much for being here.
Okay. Thank you. I'm Cosimo Gerardi, CTO of Trisan. Welcome also from Trisan. Also, the CEO of Trisan will be present tomorrow. And so I give welcome also from on behalf of him. I'm very proud to participate in hosting this important event on Heterojunction in this beautiful place in the beautiful city of Catania. Catania has a particular significance because for us it hosts let's say the largest factory of PV module and cells in the European continent. So for us it's a very important place. And our factory, is focused on heterojunction technology. So we are very interested in discussing and also in participating in this workshop. I think it will be very interesting with many important presentation and discussion. So from my side, again welcome and enjoy the workshop. Thank you.
Okay, I'm back because I'm going to share this session, the first three speakers. We start with another very good friend of mine. I'm very happy having you here, Paola, really. Paola Deli Veneri, she's the head of the Solar Photovoltaics Division of Enea. Enea is the Italian National Agency for Solar Energy and Sustainability and so many other things. So it's really a reference for our community here in Italy. And so it's a really pleasure have the possibility to start with Paola. She will talk about is Italy the EU photovoltaics hub? What is the answer? Yes. Okay, thank you so much.
Okay. Can you see my presentation? In the meantime, good morning to everyone, and thanks to the organization to give me the possibility to open this beautiful workshop in a beautiful place. Is very important, and I'm very honored to open as an Italian research this workshop. I and my colleague David Moser decided for this title is an ambitious question that we posed. Is Italy the European photovoltaics hub? Then at the end of this presentation, maybe that we can answer yes, I hope. Okay, Enea, just a few words about Enea, is the Italian National Agency for New Technologies, Energy and Sustainable Economic Development. Some numbers are reported in the slide. We are organized in many departments. We are in Energy Technologies and Renewable Energy Source Department, in particular in the Vision Solar Photovoltaics Division that is located part in Portici, where I am, here our center, and part in Rome. EURAC, where David Moser is the head of photovoltaics energy system, is an institute for renewable energy located in Bolzano. Here are some of the topics and the number of EURAC. Okay, so all of us well known the increase, the amazing increase in the photovoltaics in the world with a lot of installation, increasing global photovoltaics capacity in the contribution on energy demand and with the benefit that photovoltaics has on climate change impact. But what is the situation now in Italy? Also Italy followed this trend because we can see that in the last year, in 2023, we installed about 5 gigawatts. Then photovoltaics cover about 10% of electricity demand in the last year. That is a percentage a little bit higher than in the rest of the world. Then in Italy the situation is favoring at the moment. And for this reason, thanks to the results of the last year obtained in the last year in terms of new capacity installed, Italy is again in the top countries. Italy was missing in this ranking since 2013, and in the 2023, Italy came again in this ranking thanks to the installation, and is again in the top 10 for cumulative capacity. Some number about people plant in Italy. We have about 1.6 million of plant installed at the end of 2023 with this capacity spread in Italy in this way. We can see that most of the plants, 94 of the plants, are quite small, with power lower than 20 kilowatts. We have few very big plants with power higher of megawatts. And this is the evolution of different type of installation. Again, the increase is most of the plants are devoted to integrated photovoltaics, in particular rooftop, because we have some limitation in the installation ground-mounted photovoltaics, because regional regular are quite strict. We have a lot of limitation. Then we have an integrated PV system in our country. And here you can see the decrease of the cost of installation during this period, with a lowering of more than 80%. How is planned for the next years? The Integrated National Plan for Energy and Climate impose to reach 80 gigawatt at 2030. This means that we have to install 7 gigawatt per year. Then we have to accelerate the installation, but we are on track, because in this year, 2024, the number are right. And at that time, we think our target is that 65% of electricity will have to be generated from renewable energy, and half of that will be photovoltaics. how to help this transition, how to help this number, the reaching of this number. 2 months ago started the plan called the Transition 5.0 plan that with the purpose to support the process of digital and energy transformation of enterprises. In this context, PIBU system costs are eligible if modules are produced in Europe with certain efficiency, and the tax credit have a different level. The maximum can be obtained in this case if module and cell are produced in Europe, and in particular if cells are realized with bifacial silicon heterojunction or tandem solar cells. Then we are in the right place for this, with a value of efficiency for sure. Another measurements that try to favor the installation, the integration of photovoltaics in several contents is a measurement in the framework on National Recovery and Resilience Plan, where a target of power have been imposed for new innovative agrivoltaics or agri-solar system, with the number that you can see here. But in this context, which is the situation in European, here the landscape for the European silicon manufacturing industry is not so good. We would like to see more dense dot in this map and bigger dots. And if you the production is completely insufficient if you think that only Italy have the target to install 7 gigawatt per year. You can see that this quantity of module produced in Europe is completely insufficient. That we have to improve this situation and to gain the better position for European industry. How is one of the problems for sure is the price, the sustainable price for module in Europe. In this study you can see that if you produce all the module considering locally value chain, we can see that module sustainable price in 3 locations of Europe are over than $30 cents per watt. This is very far from the market price that maybe is not sustainable at all, but the situation, the current situation is that if we consider to use imported cell, the situation is better because we have a module sustainable price of around $20 cents per watt. But Europe have access to energy from PV, but he need also to produce, to access to the means to producing the photovoltaics generating devices. Then maybe a premium for European governments is necessary at the moment, and we have an initiative, Net Zero Industry Act, that has the purpose to boost the competitiveness of industry for decarbonization. That would be a good occasion to promote this premium. In Italy, few years ago, we have worked to create a network, the Italian Research and Development and Innovation Photovoltaics Network. The purpose is the commitment of this network is to map, to better understand the situation of the research in Italy. Here the dots indicate all the location where university research, public research carried out research on photovoltaics, in order to better coordinate this research, to use in a useful way all the infrastructure available, and to also the industry is part of this network offshore, and to better connect the research with the industry. This was an action that we started and that continue. At the moment, considering also the situation that we have, the favorite situation that we have with some new initiative in Italy. For example, here I have to mention, first of all, Trisan, but I wouldn't spoiler the presentation of Cosimo that I just mentioned Trisan, but Cosimo will give details. Maybe that some information is already held in this slide. But we have also some other news in the Italian photovoltaics content, because a couple of weeks ago, Futurasan have a good news from European Commission. They won an innovation fund for the project Fenice that include have the target to create a new factory in Veneto, in northeast part of the Italy, for with an annual production capacity of 1.4 gigawatt with benefit using fully powered renewable energy in the factory. That is, it was a very good news. And another one is related to a Lithuanian company, Solitec, that is planning to create a new factory in the south part of Italy, in Campania, with a production capacity of about 600 megawatt per year. Here the sign of the contract of the development between Solitec and Ministry of Enterprises and Made in Italy. We hope this will be a concrete action. And regarding the expertise in Italy, we can see that if you think at knowledge ready for upscaling, starting from the expertise in research, in all the research aspect related to photovoltaics, we have a lot of knowledge, both in silicon-based and also on thin film. Materials, deposition processes, equipment for manufacturing, and so on. Also for new concept. But when we go to upscale, to look from research to industry, we have also some part of the value chain. Again, Futurasan, Trisan, for solar modules, for cells and modules, applied materials, RISE technology for equipment, and so on. A new initiative, Solartics, in order to think for terminal tandem concept. But we have also some red, green lights that become red. Why? Because we in this context, the value chain is not complete, and Marco. And a discussion is ongoing to understand if it's possible to involve the remaining part of the value chain and make more light traffic green. The problem in Italy, we identify, as a research community, we identify a problem. We have a lot of activity at low TRL, but we have this dead valley. We need to fill this gap, favoring all the research on low TRL toward high TRL in order to better connect research with industry. We identified the necessity in Italy to have at least 2 national facilities for industrial prototyping. That could be a place where university research center can improve, can try to increase, to upscale their results. As a PV community, we published a document on this topic, and we hope and we are starting a discussion with politics ministry to find the right occasion to create this we can call pilot line for several aspects, maybe utility scale, high efficiency, or integrated photovoltaics. I mentioned some of the topics. This list is not exhaustive of the research in Italy, and some of images from our lab or prototype realization. And we have not a time, it's impossible to give an outlook of the research in Italy. Just I have to mention our research on two-terminal perovskite silicon tandem solar cells with some results obtained in cooperation between Enea and the University of Tor Vergata. We are working on both monolithic and mechanically stacked tandem cells with these results. This is a state-of-art, Italian state-of-art results for this kind of structure. We obtain also in Italy an efficiency higher than 30%. On agrivoltaics, Enea is involved a lot in promoting this approach, also considering the problem that we have to install our system on ground. And here are some of the examples that we are studying. Here on the right, a demo that Enea have realized in Scalea with an elevated fixed PV plants with lemon trees. And on the left, an algovoltaic system, we call that algovoltaic because there is a photobioreactor here. This system was realized in cooperation with Enel Green Power. We both cultivate algae and integrate this system, these photobioreactors, under a standard photovoltaic system. I conclude with just to mention research in EURAC with the creation of a versatile photovoltaics prototyping platform. This just to follow the discussion I mentioned before, the possibility to create a sort of facilities to integrate new study, new components on. And I will finish giving my personal greetings, but also on the behalf of Italian community. Here you can see most of the Italian PV community that in the second national conference of Italian network photovoltaics that was held in Bolzano last June. The next one will be in Naples in May, next May. And we hope that, and I hope and enjoy the discussion during these 2 days. Okay.
Thank you, Paola. Thank you so much. So we have time for a question. No question. Well, actually, I know about all the things that you have presented. Somehow, they also involve our work together in the project. So, you say that we have the right numbers. So we can really reach this 7 gigawatts in 1 year, no?
Yeah.
What is the situation in the other European countries? So are they running also fast as Italy is doing, or is different? I don't know.
I don't know the
So
exact
the
situation,
general
but
European situation.
But our measurement, our national measurement, such as the national plans, is in agreement with the European address. That I think that European has give us the target, and then all the countries moving toward reach a good installation in Europe. And we hope that Net Zero Industry Act will promote industrial action to forward this target. I think so.
Because the real question is Italy somehow in real agreement with the other European countries? Are we working all together to reach a specific goal? As in other countries, you know, if you take the United States or China, Asia.
Europe can do this.
We are so many countries with so many different, but are we able to really?
Yeah. I think in Europe we coordinate the action, at least in European country members, but we cannot assure the global. And then at the end, I forgot, I hope that my question is Italy, the European photovoltaic hub, can have an answer yes, or at least maybe, I hope so, okay?
We all hope so. Thank you again, Paola. Thank you so much. So now I have the pleasure to call on the stage Wenjing Wang. I hope the right pronunciation of your name. He is the chief scientist of Wasan, and so he will talk about the progress of heterojunction solar cells in China, which I think is a hot topic for everybody.
Thank you, Mr. Chairman. I'm honored to have this opportunity to introduce some progress of HJT in China. I'm from the Washington. So the first, we will talk about the roadmap of HJT's technology. So up to now, we already close to the three generation. From the very beginning, the double-sided silicon thin film is amorphous, but right now already become a macrocrystalline. In the front side is macrocrystalline oxygen doping the N-type thin film. But the back side is nanocrystalline silicon, nanocrystalline silicon thin film. So right now the efficiency already arrived to 25.5%. So right now we still, based on this structure, the structure doesn't change anymore, but there is a lot of small improvement for this kind of structure. So the efficiency already for mass production, average efficiency already arrived to 26.5%. And the other is reduce the cost. So we can beginning to use copper to replace silver. The next generation may be the BC, further increase the efficiency. And the next is tandem cell. So for the HJT capacity increase in China and also in Huashan, after 2021, increased very fast for the capacity. Up to now, already to the 31 gigawatt capacity installed. And in Huashan, we already installed 20 gigawatt for the mass production. Right now, the efficiency still keep the highest lab efficiency is still 26.81%, not increase more. But recently, the LONGi already arrived to the 27.3% for HPC, not for the HJT. So it's this lab. But in the mass production, they still have a gap. There's some test system for Chinese is in production is 26 right now, already 26.5% is dominate the test standard. So, but according to the ISFH, the efficiency is almost 25.6%. So we have a lot of technology improvement to get this kind of average efficiency for mass production. So we ever use a double-side microcrystalline silicon thin film, and we use a low rate CVD, and we use a silver paste, and with a steel mesh for screen printing. So, but for the mass production, because you have to consider the cost and the efficiency, you have to try to balance this kind of equipment problem. So maybe you have to build use a PECVD process faster, and also you use Cooper silver paste, and maybe use steel bath. It can be used in the mass production. So the efficiency a little bit decrease. So for the real mass production, not a golden line, is about 26.3%. But we still have a technology to further increase the efficiency for mass production, such as maybe we can use a back polish, and we can use RPD to reduce the degradation, to reduce the damage of the silicon. So maybe further can increase the efficiency to 26.7%. So here's some example of the generation 1 efficiency is around 24.3 to 5%, and generation 2 is around 25 point. This is very mass production. Is a few million wafers. For the golden line right now, for double side, already arrived distribution of efficiency arrived to 26.4 to 5%, to 0.5%. For the mass production, not only golden line is about 26.1 to 2%. As to the module power, right now for this is G12 66 wafers module. This kind of module, the power already arrived. We can sell this kind of a module. Is 715 watt per module. Right now, recently, almost arrived 720 watt. And for the lab module, power keep increase. There's a few Chinese company, the different time, they can right now the highest efficient, the highest power for that kind of module arrived 765 watt, and the module efficiency arrived 24.62%. Recent few days, even for the Tongwei already more higher power. For the mass production of the HJT cell, not only consider the efficiency. You can in the lab we can see they still have a big gap between the mass production average efficiency to the water record efficiency, the lab record efficiency. And the problem is we have to reduce the industry value chain for HJT. Some technology cannot use in the value chain technology just used in the lab, such as TOPCon, traditionally solar cell like TOPCon or PERC, such as we have to use such as for ingot, we just try to use a CCZ to replace the RCZ. For the wafer, we make a more thinner wafer, and some use a gathering method, new gathering method, and with a cheaper wafer. And the cell, we have to improve the structure, improve the electrical system, And for the module, we will talk about later. We were keeping improvement for the module, such as we use prevent the increased stability, and we use the low cost, such as zero bus bar. So first we talk about the wafer. So for the wafer, there's a novel technology, such as we can use a higher oxygen silicon wafer, such as for this in the middle, the figure in the front, in the top, in the ingot, in the top area is the hydrogen density is high. It cannot be used in the top count because the top count the process temperature can be arrived 1050 degrees centigrade. So it will be OSF or ring, but our HJT cell is only low temperature, below 200 degrees centigrade. So we can use that high oxygen density wafer, so that will be cheaper. And also, we use a half-cutting technology. Before we make a solar cell, we use a half-cutting. So it's because we use the chain process, so we can use a half wafer. So that situation, we can use the edge cutting. We can get for round ingot, we can get more wafer, and we can use chain gathering, such as in that. Sorry about some Chinese curve, but this chain process for gathering is only 2 or 3 minutes for process can diffuse the phosphorus. But if you use traditional tube type diffusion phosphorus, you have to use 20 to 30 minutes. So from 20 to 30 minutes to 2 or 3 minutes. So it's very quickly. So that's we use a new type of chain gathering system. And also we use a very thin wafer. Right now, for mass production, it's already about 110 micrometer. And recently we try to use 100 micrometer. So it's we're saved more silicon. So the next we talk about the cell structure. So for structure in the lab is not so difficult, but for mass production, you make a narrow distribution of the efficiency. It's quite different. We have some novel technology for microsupply, such as we use VHF. So we have to overcome the electromagnetic interface, and for the PCVD system, the chamber inside, we have the 3 kinds of uniformity, such as we have to use the plasma uniformity, the gas flow distribution uniformity, and for the temperature uniformity for whole of the substrate. Such as for plasma, we have to use hyperboloid type electron. It's a kind of curved surface of electron. It's a complicated surface. It's because if you use a VHF, there has a stationary wave. They may be not uniform for plasma, but if this kind of electro shape, maybe you can make a more uniformity. And also you use for the gas flow distribution, we have complicated the shower system to make a more uniform of the gas flow. And for temperature, you have a very good design for substrate temperature heating system. And for the eye layer, we have we separate only 2 or 3 nanometers that can eye layer. We separate a few layers, such as we feel I0 layer, I1 layer, and I3 layer. In the I0 layer, we put more hydrogen inside, so that will be prevent the epilepsy and also the more gas to passivate the degradation of the surface. And for I1 or I2, you have to reduce the hydrogen to make a more high quality of the surface of the wafer. And there is temperature uniformity of the wafer. When you put the substrate carry with the wafer inside the chamber, the temperature should be changed because you in the outside of chamber the temperature degree, but you inside the chamber you have to decrease a little bit of the temperature, but for our very quickly decay time, so very short decay time, so we cannot wait a long time. So the temperature inside, the temperature on the wafer, one wafer, it's maybe not uniformity. So maybe if it's too quickly, so will be some like an egg, some edge is dark or center is dark. So that's the temperature not uniformity. So maybe we have to solve this problem. In a lab, there's no this kind of problem. You can wait enough time. But for the mass production, you have enough time to waiting. So such as we get for our tools, PECVD tools, if we use decay time is 80 seconds, its distribution is quite good and efficiency is high. But you use a shorter decay time, you can hurry up, maybe the efficiency become lower and distribution become wider. And also for PVD, you have to avoid to distribute the damage of the surface of the so for such as we have to increase the field, the target field, that will be reduce the target power. If target power voltage decrease, that will decrease the damaged surface, so that efficiency will be increased. And also the other method to reduce the damage is use low power. But if you use low power, there will be decreased the rate, deposition rate, and also there has some phenomena of a target node. So that's a problem. So right now the trend is to use a high magnetic field target. And also for the edge, for the backside, we have to some edge. There's no ITO, but this ITO, if the ITO for whole of the back surface, there is some shunted, some leak for front and backside. So it's will be the fill factor will be degree. But if there is too wider of this no ITO area, will also decrease the fill factor. So we have to from the edge wedge from the very beginning is 0.5 millimeter, reduced to the 0.55 millimeter. So increase efficiency to 0.1%. But we further decrease the width of this no ITO area to 3.35 millimeter. The efficiency can further increase 0.5%. But it needs automation very precisely. So sometimes it's too narrow for the holder. There were some wafer can be low, can be go down. And the next is a package, is assembling for the reliability of HDT solar cell. There's no LID, no PID, but there is a UVID, UV degradation, and dark degradation, and the temperature degradation. So the main problem is the UV degradation. So for the cell we make a test, the UV degradation decrease. But if you use a height and heat heat and the light, they will recover totally. So the main reason may be the UV energy can break down the surface, the silicon and the hydrogen band, so make to make more diagonal band to have a minority recombination. So we use a special design of the down conversion material to put into the EVA or EVE to convert the UV to the blue light, so that if we put to cut down the enough low of the UV light, there will be the UV degradation will be totally not observed. So we also can use a UV cutoff film, but this kind of film can decrease the power of the module. Originally, at the beginning we used the UV cutoff film to only cut off the 360 nanometers. The wavelength is good enough, but recently we find out we have to cut off more longer wavelengths UV light. Because why this happened? Because we use more thinner and thinner buff layer, and we use eye layer is become thicker. So such as if at the very beginning, if we use totally amorphous silicon solar cell with a very thick totally amorphous silicon thin film, at that time is 23%. It's quite stable for UV. But if we, for the front side, we use oxygen, nano-crystalline silicon oxygen, there's more UV light go inside. And we use multi-layer of eye layer. For I0 will be decreased a little, the thickness of I0 decrease a little bit. So the efficiency, not only because of this, but maybe other together, the efficiency to arrive 24.3%. So there's a UV degradation. So it's we have to use 360 nanometer cutoff UV film. But if we further to reduce the efficiency, the thickness of the I0, and at the same time other improvement, the efficiency arrive to 26%. We have for that kind of UV cutoff, they still have we can observe the UV degradation. So we have use the UV UV cutoff thin film is up to the 380 nanometer. So it's become UV stable. But recently we further to reduce the I0, and the efficiency further increased to 26.4%. And even use that kind of UV cutoff film, it cannot. They still have a new UV. So there's a trade-off. If you want to increase the efficiency, you have to have more complicated eye layer, but at the same time, the UV stability will be decreased. So you for the mass production, you have to make a balance. According to Takuchi, Japanese scientist Takuchi, they think about after the 220, they still have that kind of UV can cause. Okay, thank you. Very quickly. So it can observe the UV degradation. So maybe in the future we further increase the efficiency. Maybe the UV degradation will be. You need to cut off higher wavelengths. So for darker degradation, we find out also trade-off. If we want to increase the efficiency, we have put more oxygen inside the N-type layer, N-type or macrocrystalline layer. But that will be cost dark degradation. So we have to use make a balance between the efficiency and dark degradation balance. And also recently we find that the new mixed frequency technology, we use 40 megahertz and 31.456 megahertz. It can make degradation, dark degradation become low. So that will be, we can use even higher oxygen degradation. The next few words is about copper replacing. We use a different screen printing. We use nickel mesh and steel mesh. The shape of the electrode become better. So we use copper with steel mesh screen printing. The efficiency can be increased 2.5 to 5%, and the usage of the consumption of the paste will be decreased. And also right now the copper, the silver consumption per watt is around 2 to 5 milligram per watt. And zero bus bar, there's two kind of, because I'm not so just have to hurry to run. So it's this kind of zero bus bar. It's already mass production in China. So finally, we're able to summarize. We have to balance the three things. One is the efficiency, the other is the low cost, the third is reliability. The different things, there is different technology. We have to further improve this kind of different technology to rebuild total value chain for match the HJT technology. Thank you.
Please. Okay, thank you. I apologize for it. Unfortunately, the time is really. Myself, I would have at least 3-4 questions for you, but we are really in delay. So, if you don't mind, I would ask everyone to make questions during the coffee break in 20 minutes. So we have enough time, coffee break, lunch break. Really, thank you. I found, as I told you, at least 2-3 points that I would like to discuss with you. So I probably think that many people have questions for you. So we stop now for the moment, but okay? Thank you so much, because otherwise we are already in delay. So next speaker, Cosimo Gerardi, once again, Cosimo. He's a Chief Technology Officer of Trisan, and will give us a perspective of the local Sicilian, Italian industry on this field. Thank you.
Thank you, and I'm very honored to participate to this event. I'm CTO of Trisan, and I will speak of the European side of the manufacturing. We are focused on heterojunction, and I will speak about our initiative in terms of manufacturing at the gigawatt scale. First of all, we share the opportunity in Europe. Of course, the market is growing, and we expect global installation to grow very much in the next year, at least also around 800 gigawatt by 2027. And in Europe, we expect a very good growth in terms of installation. For this reason, we think there is a very good opportunity for European market. Looking at the distribution across the EU between the three main segments, we expect 60% of volume are dedicated to distributed generation, and more than 30% of volumes for utility scale. This according to Solar Power Europe source. In Europe, it's very important also the let's say, what Europe is doing to support the production, and it's Europe has launched the initiative to reduce the dependency on non-European suppliers, but at least 30% by 2030. And Trisan, of course, is the first PV gigafactory in Europe, and we are very committed to produce and to produce for the European market. Of course, it's very important, what has been said before, the Net Zero Industry Act in Europe that can give some support in the production of in the supply chain of production in Europe. Trisan, as said, is a 3 gigawatt capacity factory. It is located here in Catania, in what we call the Etna Valley, because we have there is a big experience in the field of semiconductor because of other companies specialized in microelectronics. We are strongly committed to research and develop, especially the heterojunction, in terms that we are already in production, and we are exploiting research on tandem technology in collaboration with the CNS, the French Research Institute. And for this reason, we think we are leader in European manufacturing in the field of photovoltaic. We have invested about 1 billion in terms of capex and opex. Trisan is a company from Enel Green Power, so it's our mother companies giving us support in the first phase, and we had some let's say support from European Innovation Fund and the Italian Contratto di Sviluppo, about 190 million euros. We think we will arrive at least 1,000 direct jobs in the 3 gigawatt production for cell and module, and about 1,000 indirect jobs that will be created all in Catania and in Sicily. And so we focus to reshore a resilient PV supply chain in Europe. Our history, we were born in 2010 as a joint venture between ST Microelectronics, a microelectronic company, Enel Green Power, and Sharp, and started with production of thin film technology, amorphous silicon. So we have started since 2010 let's say, to know the characteristics of amorphous silicon, and in 2018 we started with the new heterojunction production. Was a 200 megawatt of production that we have, let's say, produced module for internal use for Enel Green Power that is installed especially for utility scale installation. We started also in 2020 to achieve high efficiency and to have also record in terms of efficiency of bifacial cells. We have produced so far mostly bifacial solar cells and bifacial modules. In 2022, we decided to switch from 200 megawatts to multiply by a factor of 15 to 3 gigawatts. And so started the expansion. We have starting production we have started since for a few months producing in our factory, and we have already all the tool for the 3 gigawatt that we are finishing the commissioning, and gradually we are increasing the production of cell and module. In 2023 we have launched our product that are mostly B6, that is for the utility scale, and 40 for the residential and commercial industrial. We have started in these months the production, so we're very, let's say, committed and very involved in this period, and we are working to go to the complete full capacity of 3 gigawatt, and in parallel we are working to increase the efficiency of the cell, improve let's say, to make more cost effective our production, reduce the cost compared with the market, and we are working also on the development of the tandem technology. The factory, it is around 150,000 square meters, which include offices, two main building, the B, that is the building for cell production, and C is the building for module production, and a part of the facilities. So it's a factory that produces both cell and modules. Some numbers, 3 gigawatt means 5 million modules that are produced per year, 14,000 modules per day, and 300 million solar cells produced per year, and 800,000 solar cells produced per day. So this means quite a high number. If 3 gigawatt are not so big in China, but in Europe is a very important and quite impressive number. And the factory is state of the art, is with very high automation level and also high digital control. So we have full automation. Also we are helped by the fact that heterojunction has few process steps, and for this reason we can control better the process, but also in the module line, very important manufacturing execution system, and all tools that allow us to use artificial intelligence, machine learning to control and to analyze the production and the data. Heterojunction, of course, this is the workshop of heterojunction. We think that heterojunction is a very important technology because, to my opinion, of course, it has more margin to increase performances and also to reduce the cost. First of all, because we can use very thin wafers, we can have higher performances not only in terms of efficiency but also in terms of production, average production, because of bifacial behavior, because of the low temperature coefficient. And in terms of manufacturing, we have a streamlined process flow with high technology content, but with few operations that can help in the control of manufacturing. And also we can produce quite reliable modules with higher energy yields that can have a very high durability, and so best margin in terms of efficiency improvement. Many advantages that I have told before. We are working to reduce as much as possible the thickness of wafer. Of course, the main issue is to try to reduce the scrap, especially in the assembly. And so this is one important topic. And for the cell, we are working to improve the passivation, the interface that can increase the efficiency, but also the stability, the thermal stability. The other aspect is the mechanical also stability, because we can have a very thin wafer in production. As I told before, we have streamlined the process flow compared with TOPCon, and this is, I think, an important advantage. The other advantage is that we use low temperature, that is below 200 degrees, and this can help in terms of mechanical stability and properties of the silicon. And using thinner wafer is easier for heterojunction compared with TOPCon, and also it's important that we can use, as was told before, silicon wafer with, let's say, we have not necessarily a big control of oxygen concentration because of the low temperature of the heterojunction process. And last but not least is the compatibility with the tandem technology, because of course the heterojunction can be continued as a bottom cell, can be implemented in an easier way compared with the TOPCon in a tandem process. Some results of what we have produced so far. These are modules that are in the Atacama Desert, which we can show that the blue is Trisan. Comparison with other technologies, we can see higher average production. This is from August of 2022 to June 2023, and this is in very harsh environment in Atacama in Chile. And also very good reliability. That means 3 3 times let's say what is stated in the norms for the 1,000 hour. We can achieve 3,000 hours for the heat test and 3 times the thermocycle without keeping within the maximum degradation that is 5%. And what is the path for improvement of the heterojunction technology, which is of course improvement of the wafers. That means reducing the wafers that can help in reducing costs, and the fact that oxygen has less impact because of the process of heterojunction is a low temperature. The interface between crystalline silicon and amorphous silicon, that is also the introduction of nanocrystalline silicon doped with oxygen in, let's say, both for p-type and n-type. The importance of TCO that has been mentioned before. The metallization is a very important step because heterojunction is a low temperature process and is, let's say, it's important to reduce as much as possible the amount of silver. And this is challenging for heterojunction, but there are, let's say, the possibility of reducing using zero bus bar and new, let's say, also interconnection method that use foil with wire. This is important that we can use less silver, but also using copper. First of all, using silver copper paste, and in which we reduce the amount of silver, and then also going to, I think there's some noise, going to the direct plating of copper. There will be some presentation of also in this day. And other important aspects are the assembly. First of all, the interconnection, but also the encapsulant. Encapsulant must be very resistant against moisture. Of course, we cannot use simple EVA, but we have to go to POE. But there are evolution like the EPE, that is EVA, POE, and EVA, that can also allow protection also against UV, but also can use downshifting to, let's say, shift the UV in light that can be used by the silicon. The importance of the interface, this has been also published from Longi and from a group of TU Delft. It's very important to increase the efficiency, but as we have seen before, it's very important also to protect the microcrystalline layer against the moisture, because otherwise you can have even dark degradation. For the TCO, many activities are to reduce as much as possible the indium content, trying also to introduce AZO as an intermediate layer, or to reduce, for example, the ITO thickness in the rear part of the solar cells. Other aspects are also some smart processing, like the light soaking that we have here. It is a part of our line in Trisan, which can help to increase the efficiency, but mainly to tighten, to make more narrower the distribution of efficiencies, and so to increase the efficiencies of the cell with lower efficiency. Silver, as I told, is very important. Is an important topic for all the PV. Is a must to reduce the silver consumption because of the cost, or because also the availability of silver in the world. Heterojunction is more delicate in this respect, because to be, let's say, compatible with the low temperature, we need to use more silver. For this reason, we are working to reduce as much as possible the silver, and also we can use an advantage of heterojunction that can have some protection because of the TCO to the ingress of the copper in the silicon. So using a silver copper paste or even copper plating can be, let's say, it's an advantage with respect to the other technologies. For example, using a silver copper paste and zero bus bar approach, is it possible to reduce the cost in terms of milligram per watt usage of silver, and heterojunction can reduce the gap or even be more competitive than TOPCon that today has less consumption of silver. The future can be the copper plating. We are studying with the RISE technology that we show, I think, this afternoon presentation about the localized plating. So I don't go in detail, but it's very important because we can go directly using copper in metallization. And what I said before, the encapsulant, that's a smart encapsulant. This is, for example, for hybrid, which we can shift the wavelength and can shift the transform the UV radiation in radiation that can be used by the silicon, and increasing the quantum efficiency, and so increasing the efficiency. This layer is important, that must be also a good protection against UV, but also against the environment, especially for the humidity. In terms of roadmap, very fast, we know that we can increase and at least achieve 27% even without the back contact architecture, and keeping all the say benefit of the heterojunction. But for going beyond, we are going to the tandem technology. Just a few two slides to show what we are doing. We are working with the CNS today at small area, because we have achieved around 29.8% of efficiency on small area cells, that is 3 centimeter by 3 centimeter of active area. And now today we are working to the scaling up using tools that can scale this process on large area. So of course it's very challenging, but we think the tandem is a step that must enter as soon as possible in production to be competitive in the PV market. Some interesting things that we are optimizing the structure. We can have good resistance against electrical stress, especially in reverse bias. This is good because perovskite alone is quite weak in these terms, but perovskite on silicon can have more robustness. I think that the activity is very important, the scaling, of course improving the stability and the reliability, and we are working quite hard with the CNS in this activity of development. I think that I have finished, so thank you for
Thank you. You save 45 seconds, so you deserve one question eventually.
I have a question of two.
Oh, yeah, there's a question over there. Sorry.
I'm Shravan from Tang News. So can you say a little bit about your commercialization plans? So, earlier you were mostly consuming modules for your own self. So how much of your production capacity?
Yes. Let's say, we have a nominal capacity. We will arrive in 3 gigawatt, but not this year. We will grow gradually. We think to increase and to go around 1 gigawatt next year. Our main target today is the commercial and industrial. This is a target that is, we think is a good target for European market. And for this, there are also some incentives in Italy, and we expect also some from Europe. And for this reason, we are going in this direction. We are producing now module, so I think starting, we have also receiving some order.
Okay, thank you. So as for the previous one, I would leave the coffee break for the right time to interact, to make questions, discussions. We now have a half an hour coffee break, but before I would like to thank all the speakers again. Thank you so much. So the coffee break is downstairs. There's a very nice cloisters, and you can enjoy half an hour relax and discussion. Thank you so much.